Okay. There's a little thinning that went on here in the student population. That is, must be a holiday. Okay, so a joint distribution function looks like this. You have two random variables, and you might be given this function, which is called the joint distribution function, and it gives information about the statistical behavior of the pair and how they are related to each other. You can find the marginal distribution functions by summing over y in the discrete case, or by integrating over y. Well, I'm sorry, letting y, I'm sorry, oh, I was doing the density, sorry. Taking infinity here. This is in both cases. Okay. In terms of densities or probability mass functions, so did everybody see this? I have an office hour today. Okay. So this is the PMF for the random variable capital X. This is the PMF for the random variable capital Y. If X and Y have a joint density, that is, we're talking about the continuous case, both are continuous random variables. Then the marginals are given by integrating. Let me call it little f, sorry. The marginal density for capital X is the integral of the joint density in the y variable, and the marginal density for capital Y is integral in the x variable of the joint density. And then we also looked at conditional PMFs and densities. defined in a natural way. And then finally, we introduce the notion of independence. Yeah, question?
For the joint or the marginal.
Oh, yes, here, I put the wrong letter here, didn't I? dx, sorry. Thanks. If the joint distribution function factors into the product of the marginals, then we say that the random variables are independent. This is really analogous to independence for events. There we said A and B are independent if probability of A intersect B is probability of A times probability of B. By definition of the joint distribution function, this is equal to that. Think of that as being the event A. This is the event B. What do we have on this side? This thing is that. This is the probability that y is less than or equal to y. So this is the probability of A again. And here's the probability of B. So probability of A intersect B is equal to probability of A times probability of B. So it's the same as the old case. And there are ways to check independence. If you have the PMF or the joint density, if the probability mass function factors into the product of the probability mass functions, then the random variables are independent. In the continuous case, if the joint density factors, then the random variables are independent. So that's a little review of what we've done so far in this chapter. Okay. A lot of times random variables are added together. And so it pays to understand how the what's the distribution of the sum of two random variables or more. So let's say we have two random variables x and y which have joint PMF. And let's assume that x and y are integer valued. So an example of that would be Poisson random variables, or Bernoulli random variables, or binomial random variables, or negative binomial. Or geometric. But this is just for simplicity. The formula still works for non-integer valued random variables. What's the PMF of x plus y? Well, the PMF of a random variable, x plus y, again, is a random variable. It's just this function of z. So we have to express this somehow. In terms of what? Well, the only thing we have to express it in terms of is the joint PMF for the pair xy. This is the probability that capital X is little x and the capital Y is little y, right? So that we have to try to express it in terms of that. That's usually what's given. So how can capital X plus capital Y be equal to z? Well, capital X must be something, and then capital Y must be something, so that the two are equal to z when you add them up. So this should be a sum over x, p of x, z minus x. If I add x and z minus x, what do I get? Z. And what is this? This term here is the probability capital X is little x, and that capital Y is z minus little x. If I sum over all x, then I get all the possible ways that x plus y can add up to z. If x and y are independent, then the PMF factors and the formula for the PMF of the sum becomes and a fancy term for this is the convolution of p sub x and p sub y. It's called the convolution. See, I just copied this formula down, but I replace this by p sub capital X of little x and p sub capital Y of z minus x because there's factors when they're independent. So I just wrote down this formula in the case where I substitute here x and there z minus x. Okay. So let's do an example. Any questions so far? Okay. Well, let's do this. If x and y are independent and x is a Poisson random variable with parameter lambda and y is a Poisson random variable with parameter mu, let's find the PMF of x plus y. Okay, so the independence statement is that pxy factors into the product of the PMF of x and the PMF of y. And the statement here is that the first term is lambda to the x over x factorial e to the minus lambda. And the second one is mu to the y over y factorial e to the minus mu. And what values of x and y do we have here? X could be 0, 1, 2, etc. Any natural number. Same for y. 0, 1, 2, any natural number. Okay? Okay, so now we have to use this formula. All right. Let's first try to decide what the limits of this sum here are. Here we say this variable and this variable should be a natural number, 0 to infinity, right? So should we consider in this sum negative integers? No, because this would be 0. Okay? So x will start at 0 and go how high? Z is fixed. Some natural numbers, z is some positive natural number. And here we don't want to have a negative number, so x should only go up to z. Okay? And now let's substitute what p sub capital X is and p sub capital Y is at these two variables. Okay. Let's factor out the terms that don't depend on the index of summation. That would be mu to the z, I guess, and e to the minus lambda and e to the minus mu. So we factor out e to the minus lambda plus mu. And maybe Let's leave the mu in there. And we'd have that. Where in the numerator here, I probably should put 1. But it seems to me that the denominator is begging for something. It wants another term. It doesn't want 1. It wants something else there. It wants z factorial. Which means we should divide by z factorial out here. Why does it want a z factorial?
Because then z choose x.
Exactly. It says, please make me a z choose x. Z choose x. So what do we get when that happens? Oops, I don't need this. That's a extraneous emoticon there. Isn't that what it's called? When you put in smiles, parentheses that are supposed to indicate smiles and things like that. Okay, so that's what we get. Should we stop there? Could you recognize that? Maybe we have to simplify a little bit. What is this sum? Yeah, that's lambda plus mu to the z power. That's the, what theorem are you quoting? Binomial theorem. By the binomial theorem, this is lambda plus mu to the z. And this is good for z equal to what? 0, 1, 2. So what's the, can we identify now the distribution of x plus y? Here's the PMF. What's that called? Well, what's this one? Poisson with what parameter? No? Lambda. Or if you get confused, look at what's in the E. Lambda. What's this? With parameter lambda plus mu. So if you add independent Poissons with parameters lambda and mu respectively, you get a Poisson back where you've added the parameters. Okay? Okay, let's do a simple example with continuous. Let's go to the continuous case now. Questions on this? Oh, okay. Okay, so maybe I should make one remark before we do this computation. There are some niceties you have to observe here, but if A is a closed set or an open set, they're nice enough. So that the probability that the pair is in the set A is the integral over A of the density. This example up here is just having the set A is a set of ZW such that Z is less than or equal to X and W is less than or equal to Y. And this would be the probability that the pair XY is in the set A. But that relationship holds for almost any A. You don't have to worry about almost any, just any A you come across. And you can do this by approximating A by rectangles, unions of rectangles, and using this definition here. So to compute the probability that X plus Y is less than or equal to Z, we have to try to express this as the probability that XY is in some set A. And let me put a Z here to indicate it has to depend on Z somehow. So we have to figure out what's the set A sub Z that describes a pairs of points in the plane whose sum is less than or equal to Z. What's the set AZ so that if a pair x little y is in AZ, then little x plus little y is less than or equal to Z? Well, that, I think I just said it. This is the set A. Okay. Now let's try to write that in terms of some limits of integration. Maybe it would help to draw a picture. Well, first let's decide where is x plus y equal to z. What's that look like? What geometric object is x plus y equals z? X plus y equals z, or y equal minus x plus z. Z is fixed. Y equal minus x plus z is what kind of geometric object? A circle? Ellipse? It's a line, yes. And to draw a line, you only have to figure out 2 points on the line and then connect the dots, right? So what 2 points are on the line x plus y equals z? Okay, so 0, z. And I suppose z0 is another good candidate. And so x plus y equals z would be that. And where are the pairs whose sum is less than or equal to z? Well, this is one side of the line. This is one whole half plane lying on one side of the line. Which side? The bottom part. Because in this picture, 0, 0 is in that set, right? It looks like I have z as a positive number. So it'd be this part here. This part here is az. Okay. So how can we describe AZ when we want to integrate? I think you can let x go from 0 to infinity, because x does go, I'm sorry, from minus infinity to infinity. X does go from minus infinity to infinity, doesn't it? But for a fixed value of x, what does y do? if I fix a value of x here, y goes from here, or from minus infinity up to here. And what would this point have for its coordinates? First coordinate is x. Second coordinate is z minus x. So y would go from minus infinity up to z minus x. And we're integrating y first here and then dx. And I want to change the variable here. I'm going to set y equal to v minus x. So x here is being fixed. V is the new variable. dy is dv. And then probably that capital X plus capital Y is less than or equal to Z becomes, well, I didn't change the X. So we still have integral minus infinity to infinity there. But here, what are the limits in V? When Y is minus infinity, V should be minus infinity as well, right? When y is z minus x, v should be z. Okay? And now,
should it be v minus x inside the function?
Yes, thank you. Yeah. So for y, I have to put v minus x. Yeah, y is v minus x, so it goes here. Okay. Now, that's the distribution function for x plus y. What would the density be? How do you go from distribution function to density? You differentiate, right? So the density would be obtained by differentiating this expression with respect to z. Where does z appear? In the upper limit of integration. How do you differentiate an integral? What's that equal to? That's h of z. It's h of z. So we just evaluate where? We evaluate this function. We're integrating here with respect to v. So we just evaluate this function at v and then get rid of the integral. And you have that. Okay. So here's the distribution function and the density for the sum of two random variables with joint density little f. Now let's consider the special case where they are independent random variables. Okay, and this expression here is called the convolution of f sub x and f sub y. So let's do a couple of simple examples. Suppose you have two normal random variables. They're independent. They're normal with mean 0 and variance 1. What is the distribution of their sum? So that means you want to find the distribution function. You want to find the probability that x plus y is less than or equal to z. Whenever you're asked, find the distribution, you're supposed to be able to write that down. And then further, if you can identify it as, say, being Poisson or uniform or geometric, you're supposed to say that too and identify the parameters. Okay, so we can use maybe this formula because they're independent. But what we need is the individual densities. The statement that they're normal with mean 0 and variance 1 means that f sub x of little x is 1 over root 2 pi e to the minus x squared over 2. F sub capital Y of little y is 1 over root 2 pi e to the minus y squared over 2. And this is for all x, for all y. That they're independent means we can use that formula over there. Here we don't have to restrict the limits of integration at all because the density for capital X is positive for all x, and the density for capital Y is positive for all z minus x. All right, now let's substitute this in here and this with a z minus x in here. We get 1 over root 2 pi times 1 over root 2 pi. So outside, I'll put 1 over 2 pi. Both terms have an e, so I'm going to just use this. When I multiply the two exponentials together, I can just use one exponential and add in the exponent, right? So there it is. But it probably can be simplified, so let's try to simplify it. And what we do know is that this is a density. That means we know that if we integrate this function from minus infinity to infinity, we get what number? 1. So that's the only thing we're going to have to use. Or if I integrate that function from minus infinity to infinity, what do I get? If I integrate that, I get 1. If I integrate that, I get square root of 2 pi. Okay? So that means we don't have to do much work here. Let's see if we can get this to look like e to the minus something squared over 2 in the exponent. So over here, I'm going to get rid of the minus sign and the half. I'm just going to look at x squared plus x minus z squared. Okay. Let's multiply this out. It becomes that. Add the x squared terms together. I get that. I'm going to factor out the 2 here. And in this term, I'm going to complete the square. How do we complete the square here? This is a quadratic in x. So I look at the coefficient of x, which would be minus z. I divide that by 2. That would give me minus z over 2. And I square that. That would be z squared over 4. So what have I added in here? I've added in z squared over 2. So I should subtract it off. When I subtract z squared over 2 from z squared, I get z squared over 2. Okay? And now this has completed the square. I get x minus z over 2 squared plus z squared over 2. Okay? So I'll put that in the exponent here. Okay. Now the term with the z squared over 2 is not being integrated. We're integrating next, so I can pull that out. If I pull it out, I factor out e to the minus z squared over 4, right? And then I'm left with integral minus infinity to infinity e to the minus x minus z over 2 squared, and then 2 times 1/2 dx. And I'm going to write this as 1 over root 2 pi e to the minus z squared over 4, and then 1 over root 2 pi integral minus infinity to infinity e to the minus x minus z over 2 squared over 2 times 1/2 dx. Okay, so what does this look like here? If W is a random variable which has a normal distribution with mean, mu, and variance sigma squared, then the density for W is this. And that's what this density looks like, with mu equal to z over 2 and sigma squared equal to 1/2, right? But it's missing a little bit. It's missing a sigma squared. See, it's root 2 pi here. We need a 1/2 here, so let's put a 1/2 in there, but then we have to fix it somewhere. We fixed it here under the square root. Well, let's compensate for it over here. What should we put in here? There we put in a 1/2. Here we should put in 2. and then it multiplies out to 1 in the end. So it's the same as what we started with. Okay? So now let me put a box around this part. What is the value of the thing in that box? It's the integral of a normal mean z over 2 variance half density. And what's the integral of a density always equal to? 1. So this value of the thing in the box is 1. And so what does this whole thing equal to in the end? Just that part in front. And this is good for z between minus infinity and infinity. So there's the density. What would we call that? A random variable with that density. Well, compare with this. Does it look like this at all? Can you pick mu and sigma squared so that that's what you get, aside from the fact that there's a z and here's a w? It's just a matter of a variable of integration. Yeah, mu is 0 and sigma squared is 2. So this is a normal mean 0 variance 2 random variable. So if you add 2 independent normals with mean 0 and variance 1, you get a normal with mean 0 and variance 2. If you add 3 independent random variables together, which were mean 0 variance 1, what do you think you would get? Normal with mean 0 and variance 3. If you add n, it would be normal with mean 0 and variance n. Now, I didn't say what it means for n random variables to be independent. What it would mean that they're joint density function factors into the product of the individual ones. Okay, so those are typical examples. And there are exercises that do that. So let's take a break now. Okay. Sum of two random variables is just a special case of a function of two random variables. In the book, they also look at ratios. How would you get the distribution function for a ratio? This is another example of a function of two random variables. I would break it up into these two probabilities, because now in the probability you see first, I can multiply both sides in the inequality by y, and the direction of the inequality stays the same. And in the second one, I can multiply again by y, but this time the inequality goes the opposite direction. Okay. And if they have joint density, capital or little f, then I would write this probability as an integral like that, and this probability is an integral like this, where A1 is a set of pairs x, y, such that little x is less than or equal to z times little y, and little y is bigger than 0. And A2z is a set of pairs x, y, such that little x is bigger or equal to zy, and y is less than 0. I can draw the pictures of these two sets, A1 and A2. In the first case, y bigger than 0 means we're in the upper half plane. What are the pairs for which x is equal to zy? What pairs x, y satisfy x is equal to zy? Z is fixed. That's a line with slope 1 over z going through the origin. We have equality on the line through the origin with slope 1 over z, and then x less than or equal to that would be what? Which side of that line? So let me draw the line. Which side of the line is this set? Well, it's one side of it, so we can just test somewhere. How about at y equal 1, x equal to 0? If y is 1 and x is 0, is this satisfied when z is positive? Yes. Okay. So it's this side. So I drew this as if z is positive. If z is negative, what would the picture look like? Then I have negative slope, and I would be still on this side line. So even it'd be just move this over, and then the shaded region would be here. Okay, that's A1. Now, for A2, we're below the axis. Again, we're looking at the line x equal 1 over z. But now we probably should continue. If I were to draw this line, it should also go down here, right? But I'm only interested in the part below the axis. So here's, again, the line y equal x over z. And now I want x bigger than zy. Where would that be? Well, that's one side of this. Let's test at 0, minus 1. At 0, minus 1, what do we get? 0 here. And if z is positive, we get that it's here. So this will be A2. If z were negative, then the line would be like this, and it would still be this region between the line and the axis. Okay, so you integrate over the joint density over these two regions. Here's an exercise. Is actually an example in the book. Try to do it before you look at the example. When x and y are independent normal 0, 1 random variables, what's the distribution function of x over y? So you'd use this formula here. You could differentiate in z. You set up the integral with limits that depend on z. Differentiate with respect to z. That'll give you the density function. And what do we put in here for this? The product of the density functions for normals. That is, you put in 1 over root 2 pi e to the minus x squared over 2 times 1 over root 2 pi e to the minus y squared over 2. Okay, so try that exercise. If you can't do it, it's one of the examples in the book. And it becomes a very well-known distribution called the Cauchy distribution. Okay, more generally, you might have two functions. We can compute the density of two new random variables if we know the joint density of the old ones, x and y. And if you took 2e, which I think all of you said you've done, or you've done with high probability. In other words, if I sample one of you and asked, did you take 2e, the probability you did would be something like 0.9, I think. This uses the Jacobian, you might remember. You compute the determinant of this matrix. We'll assume it's not 0. That's from the invertibility. And then the density now here, maybe I should be a little more explicit. This is a function of x and y, because these are both functions of x and y. Okay, that's the new density. evaluate the old one at these inverse functions, and you multiply by 1 over the absolute value of the Jacobian, evaluated at the inverse of the new variables. Okay. So let's try an example. Suppose we start with independent mean, zero variance 1 random variables, and A take an invertible matrix A, and then our new random variables will be A x plus by will be u, and cx plus dy will be v. In other words, the vector uv is matrix A times the vector xy. Okay. This has this form up here. In other words, little u is, let me write it this way, little g1 of xy is a times x plus b times y. That's our variable little u. And v, g2 of xy is cx plus dy. What would h1 and h2 equal here? Well, we want to invert the transformation that takes you from xy to uv. So you want to go from uv to xy. So how can we solve this for x and y? Well, we just invert the matrix. What's the inverse of this matrix? Let me call this number delta. AD, the determinant, I'll call that delta. The inverse of this matrix is D over delta minus B over delta minus C over delta, D over delta, A over delta, sorry. Okay? You've seen this before, I think. You divide by the determinant, and then you exchange the, you can't see in the back? You think you switch these two, not these two? Well, let's check. Let's multiply these two matrices together. When I take this, I'm going to have this on the left, this on the right. So the entry in first row, first column would be this column inner product with that row. That would give me AD minus BC over delta. That'd be 1. Then I would get this times this as the entry first row, second column. That would give me minus AB plus AB over delta, or 0. So I get 1, 0. Second row, first column, I'd get this times, or let's see, I'd get this times this. That'd be dc minus dc over delta, which would be 0. And then I'd get what? This times this, that'd be minus bc plus ad over delta, which is 1. So this is the right formula. Okay. So we just apply A inverse to uv to get x and y back again. So we get d over delta u minus b over delta v. Here we get that. Any question on this? What's the Jacobian of our transformation? Well, we differentiate this function with respect to x and then y, and that goes in the first row. What's the derivative of this function with respect to x? It's a. The derivative of this function with respect to y is b. Then in the second row, we differentiate this function with respect to x and then y, getting c and d. So the determinant here is ad minus bc, or delta. And so the joint density of the new random variables is what? Well, the absolute value here would be just absolute value of delta. So I get 1 over delta. And I'll put absolute value in case delta happens to be negative. Right? There's an absolute value sign here. And then I evaluate the joint density at h1 of uv and h2 of uv. But what's the joint density in this case? It's that. Right? This is 1 over root 2 pi times e to the minus x squared over 2 times 1 over root 2 pi e to the minus y squared over 2. It's the product of two normal mean zero variance 1 densities. Now I have to evaluate this at h1 of uv, h2 of uv. So I put h1 here and h2 there. H1 is 1 over delta du minus bv. Okay, now this is going to be squared, right? So it'll have a delta squared in the denominator. And I'm going to put this in where I see y there, and this will be squared, and it'll also have a delta squared in the denominator. So let's put that delta squared down here. Okay, and now let's finish it off. du minus bv is squared. That's what goes in for x. And then minus cu plus av also squared. Okay, so there's the joint density of the variables uv. And as usual, this is correct, but Maybe we could simplify it and try to identify it. So let's work with this a little bit. What's the coefficient of u squared in the numerator here? It would be d squared plus c squared. What's the coefficient of v squared in the numerator? A squared plus b squared. What's the coefficient of u times v? Is that right? Okay. What does this look like? Does it look like anything you've seen before? I always forget. I think it's did I write it down here? Right, I forgot something here. I think that's it. Yeah. What is this? That's called the bivariate normal, right? And what does it have? Well, it has some junk out here. And it has an exponential, and it has a minus 1 over 2 times something. Then it has quadratic expression in x and y. Okay. What do we have here? Some junk out in front. And then, well, there's a minus, there's an exponential, minus a half something. And then a quadratic expression in u and v. So this is a bivariate normal. What we should try to do is identify mu sub u, mu sub v, sigma sub u, sigma sub v, and rho. So what is mu sub u? Well, if mu x is different from 0, you get a linear term in x, right? Do we have a linear term in u here? No. We don't have a u alone. We have u times v. So that means mu sub u is 0. What about mu sub v? By the same argument, mu sub v is 0. Okay? This delta must be sigma u, sigma v, square root 1 minus rho squared. Right? Because there's a 1 over 2 pi here and there. There's only an absolute value of delta there, and what's left here must be the absolute value of delta. Now we have to decide what's sigma u, sigma v, and 1 minus rho squared. Well, what do we have? What's multiplying x squared here? What's the coefficient of x squared? It's 1 over, well, aside from the minus a half, 1 over 1 minus rho squared times, oh, this should be squared here, sorry. Sigma x squared. So we get that 1 over 1 minus rho squared, sigma x squared, that's the coefficient of x squared. That must be d squared plus c squared over delta squared. Okay? Here we have a 1 over 1 minus rho squared times sigma sub y squared. That's the coefficient of y squared. That must be a squared plus b squared over delta squared. Here we have a 2 rho over sigma x sigma y. That's the coefficient of x times y. Oh, and also a 1 over 1 minus rho squared. So we get here rho over 1 minus rho squared sigma x sigma y must be or I should say, sorry, I should be doing the sigma u, sigma v. This should be u here. This should be v. This should be sigma u, sigma v. That would be what? We get a minus. If we compare, there's a minus 2 here, right? That's this 2. And then we get a rho. So rho over 1 minus 1 minus rho squared. Sigma u, sigma v is ac plus bd over delta squared. Okay. So here we have 1, 2, 3, 4 equations in how many unknowns? Well, just 3, rho, sigma u, and sigma v. And you can solve for sigma u and sigma v. Which I will refrain from doing. Okay. You can solve for sigma u, sigma v. Okay. In the book, They do the example. The book does the example where A is and in that case, it would be very easy to solve these equations. Okay, so check the book for the example where A is this. Here's what it looks like generally. So, in fact, every bivariate normal comes from a transformation of this form. UV equal to a matrix A times xy plus a vector B, where x and y are independent normal random variables with mean 0 and variance 1 even. Okay. So bivariate normals come from linear transformations of independent normals. Okay. Let's try another example. Okay, so here's the xy plane. We're picking a point randomly, xy, so that x is normal mean 0 variance 1, y is normal mean 0 variance 1. What are the functions u and v? U is just the length of the segment from the origin to xy. So in other words, it's the distance from xy to the origin. And what's the arctan of y over x? It's this angle. So we're just computing what? The polar coordinate distribution of polar coordinates of an independent normal mean 0 variance 1 pair. Okay. So in this example, g1 of xy is square root of little x squared plus little y squared. g2 of little xy is arctan of y over x. That's u. This is v. What are the inverse transformations? X would just be u times cosine v, right? That's like r cosine theta. That would be h1 of uv. And what's y? It's u sine of v. That's h2 of uv. Those are the inverse transformations. That's how you go from polar coordinates to rectangular. Except you're probably used to seeing this with r and theta. Would you rather I put r and theta for u and v, or can we handle u and v? uv is okay? All right. It's probably a little bit better because now we have to do what? we just have to compute this and then plug in h1 and h2 in the normal. Okay, so let's compute the Jacobian. We differentiate this with respect to x. Derivative of the square root function is 1/2, and then you get whatever is there to the minus 1/2 times the derivative of what appears inside. What's the derivative of the thing that appears inside? 2x, so you get 2x over this thing, right? But there's a 1/2, so that cancels. So you get x over square root of x squared plus y squared. Okay, now we differentiate that with respect to y, but just exchange the role of x and y here. Now we have to differentiate arctan. What's the derivative of arctangent of z? Right, 1 over 1 plus z squared. So the derivative of arctan of y over x with respect to x, what would you get here? You'd get a y over x squared, but then you have to multiply by the derivative of y over x, which is what? With respect to x, that's minus y over x squared. So you'd get a minus y in the numerator. You'd multiply this thing times x squared, but what is this thing? It's 1 plus y squared over x squared. That'd be x squared plus y squared, right? And a minus y up here. And what do you get over here? Because you'd have this again, but then you multiply by the derivative of this with respect to y. What's that? That's 1 over x. So I get 1 plus y squared over x squared times 1 over x. But let me multiply here by x and there by x. This becomes x squared. And then x squared times this becomes x squared plus y squared, and I get an x up here. Okay? And so we take this determinant, and what did we get? This product minus that product. Well, here's an x squared. Let's forget the denominators for a moment. We get an x squared plus y squared in the numerator. What do we get in the denominator? It looks like square root of x squared plus y squared times x squared plus y squared. I think you get cancellation, and it becomes 1 over square root of x squared plus y squared. Okay? And now we can just plug this formula in. Okay? And maybe I should be a bit more careful about how I put that minus sign. This minus sign is out in front here. Okay? This is 1 over the Jacobian. Otherwise, I evaluate the density, joint density of xy at h1 and h2. Let's simplify. H1 squared is u squared cosine squared v. H2 squared is u squared sine squared v. What happens when I combine this squared and this squared when I add those up? Both have a u squared. Factor it out. What's left? Cosine squared plus sine squared. What's cosine squared plus sine squared? It's 1. So in the numerator here, I just get e to the minus u squared over 2. And, oops, I'm sorry. Yeah. I put square root there. I didn't. It's a knee-jerk reaction. It's 2. What? There wasn't a square root here. It's just 2 pi, right? And then this becomes what? Well, it's the same computation as up here. Here we got u squared, but now we're taking the square root of it. So this is u. Where's the v? Well, what are the limits for v? What values can our tangent take? 0 to 2 pi, right? If I want to find the marginal density for u or v, what should I do? I should integrate out the other variables. So we want to find the marginal for u or for v first. How about for v? Let's find the marginal density for v. What are the limits of integration for u? U is the distance to the origin, so that's 0 to infinity, right? And what's the value of this integral? How would you do that? You could substitute w equal to u squared over 2, and then dw is u du. And so this becomes 1 over 2 pi. What about the limits of integration? When u is 0, w is 0. When u is infinity, w is infinity. 0 to infinity. E to the minus w dw. And that's 1 over 2 pi minus e to the minus w evaluated between 0 and infinity. The value of this at infinity is 0. The value of this at 0 is minus 1, but I have to subtract it, so it becomes plus 1. So I get 1 over 2 pi. So that's the density for capital V. And what are the values that little v can have? Between 0 and 2 pi. Remember, it's the arctan. It's the angle with the positive x-axis. So what's the distribution of little v? It's uniform on 0 to pi. And what would the density for u be? I integrate out the v. And what do we get when we do that? I integrate this with respect to v from 0 to 2 pi. This doesn't depend on v at all. So I integrate with from 0 to 2 pi dv. I get 2 pi, and that cancels this, doesn't it? So you get u e to the minus u squared over 2. And this is for 0 less than u less than infinity. Otherwise, the density would be 0. And again, outside that range of values, little v, the density is 0. So what else can we conclude about u and v? Well, the joint density is the product of the individual densities, right? So what does that mean? U and v are independent. So if you have pick a pair of independent normal mean zero variance 1 random variables, the angle that makes with the x-axis is uniformly distributed, 0 to 2 pi. The radius is distributed according to this density. That's called the Rayleigh density. And the angle and the distance from the origin are independent random variables. Okay, now one last thing. So we know that this random variable is uniform. Can you find the distribution of y over x now? Well, y over x is a simple function of this. It's the tangent of that. So if you want to find the distribution of y over x, what would you do? This is a problem that I said you should look at, solve, to find distribution of y over x. Take tangent of theta, where theta is uniform on the interval from 0 to 2 pi. That's what that is. This is uniform on the interval from 0 to 2 pi. We take tangent of arctan of y over x, you get y over x. Okay? So then you write down probably that the tangent of theta is less than or equal to little x. What would that be? That'd be the probability that theta is less than or equal to tangent inverse, or arctan of x. Arctan is increasing, decreasing, or what? What does arctangent look like? Looks like that, right? And then you could write down what this is. Okay, so I'll leave it like that. This is the one way you can solve that problem. So that's it for today.